In this lecture, we're going to work a large multiple unit mass balance problem. Seawater contains roughly 3.5% by mass salt in the balanced water. To produce drinking water from seawater by desalination, one process is to take the seawater and feed it to a series of evaporators. In this case, we're going to consider 10 of them. In the evaporator, the seawater is boiled, essentially, to produce a vapor stream. The vapor stream is pure water, and this is our product. What's left behind is a concentrated salt solution. It's called the brine. The brine produced by the first evaporator is sent to a second, where additional water evaporation occurs to add to our product water stream. And a brine is produced by that second evaporator as well, which is then fed to a third, and so on until we reach the 10th. And from the 10th, the brine stream that is removed is a waste product that is then disposed of. Commonly, this is sent back to the ocean, disposed in the ocean, although there is environmental concerns associated with how you treat this brine, and there's work underway to try to minimize the amount of brine that's produced, or in many cases try to eliminate it. To work this problem, you can assume that the brine from the 10th evaporator contains 5% by mass salt, and that each evaporator produces the same flow rate of water vapor. We're going to begin by drawing and labeling a process flow diagram. What I'd like for you to do is to stop this lecture and then attempt to draw the process flow diagram on your own. Once you've attempted to do this on your own, then continue on with the lecture. Well, I hope that you had stopped and attempted to draw the process flow diagram. What we're going to do is do it now together. And we're going to start off with the highlighted statement here and drawing the process flow diagram by reading again that seawater contains 3.5% by mass salt in the balanced water, and seawater is fed to a series of evaporators. I'm going to just consider the first one. In this evaporator, the water is heated, essentially boiled, to produce a vapor stream, which is the pure water, has only water in it, and a brine is produced, a concentrated salt solution. And so what I would recommend is that you would draw an object that looks like an evaporator, like this. You'll have a feed to that evaporator, and then from that evaporator you're going to produce a water product. This is going to be water only, which is a vapor stream, and then there's a brine that's produced by this product as well, which then is going to be fed on to an additional evaporator. So I'm going to draw this a little more nicely inside PowerPoint and show it to you, and then label the stream with flows and compositions. So here's that first evaporator that's been drawn with using the drawing tools within PowerPoint. So that's evaporator 1. The feed to that evaporator, to the first evaporator, is a seawater feed. We know that the composition of salt in that is 3.5% by mass salt, or 0.035 is the salt mass fraction. Since the balance is water, the water mass fraction is 1 minus the salt, so it's 0.965. This evaporator produces a vapor, which is pure water. That's a stream right here. The composition of this is mass fraction of water is 1, mass fraction of salt is 0. We don't know the flow rate. I'm going to use a variable ME to be the mass flow rate that's evaporated, and the number 1 is the mass evaporated from the first evaporator. The stream that comes out the bottom, the residual brine, is drawn here with flow and composition information. We don't know the salt composition of this stream, so I'm just going to label that X1. The 1 indicating that this is the stream from evaporator 1, and since the mass fractions must sum to 1, the mass fraction of water is just going to be 1 minus X1. The flow rate of this concentrated brine we're going to label as MB, mass flow rate of brine, and the number after the MB again indicates that this is from the first evaporator. You're going to see we'll be using these variables ME, MB, and X to represent the composition and flows coming out of an evaporator, and the number that follows those variables will refer to the evaporator that it comes from. So once you try then adding in the second evaporator on your own here, and then I will do it myself and show it to you here in the PowerPoint. And so I hope you had taken some time and have added in the second evaporator. So that's this additional highlighted text here, is that the brine from the first is fed to the second. I hope you've drawn that. and labeled it using the convention that we've talked about. So we had the first evaporator, then we had a second. The feed to the first is our seawater. What comes out of as the brine from the first goes to the second. Both the first and the second produce an evaporated water stream. ME represents the flow rate of that stream. The number represents the evaporator it comes from. The brine we're labeling MB, and the number after it represents the evaporator it comes from, and we have an MB2 coming out, a brine being produced by the second evaporator. So I hope you drew something similar to that. Once again, I'm going to show you what that looks like in PowerPoint, using the drawing tools in PowerPoint to make it look nice. So here's that second evaporator drawn using the notation that we've talked about. The feed from the first, the brine produced by the first, is the feed to the second. So we've already labeled the feed to the second evaporator after we've labeled the brine coming out of the first. We're going to use the same notation there. The evaporated water is labeled here. The flow rate of that evaporated water is ME, and the number 2 represents, that's the flow rate from the second evaporator. It contains only water, so the salt mass fraction is 0, and the water mass fraction is 1. The brine produced by the second, we're going to label MB with the 2 to indicate it's from the second evaporator, and the salt mass fraction is X2. We're going to use that as a variable, so the water mass fraction is 1 minus X2. Once again, the number here refers to the evaporator that the stream comes from. In all cases, the number in the variable refers to the number of the evaporator that it comes from. Now, this problem is initially a little overwhelming. We've got 10 different units, but by being judicious about how we label streams, we can actually do the labeling and drawing and have it, I think in the end, be fairly easy to read the process flow diagram and to work with it when doing mass balances. And so the brine produced by second is fed to the third, and so on until we reach the 10th. Why don't you take a moment and draw in the remaining evaporators 3 through 10. I would recommend that you pause right here and do that. And then after you've done that, continue the presentation. Well, I hope you took time to do that. Here's a condensed version of what you should finally have drawn. What we have done up to this point was draw and label the first 2 evaporators. And what you see here are evaporators 3 through 10. Each one is identical in terms of it produces, for instance, from the third evaporator, a vapor that is pure water. So the mass fraction of water is 1, mass fraction of salt is 0. And the flow rate, which we don't know, we're going to call ME of that evaporated water, and the number after it, 3, indicates it's from evaporator 3. The brine produced by evaporator 3, the flow rate we're going to use the variable MB3 to represent. The composition of salt, the mass fraction of salt is X3, and since the mass fraction summed to 1, the composition of water is 1 minus X3. And that just gets repeated for evaporated 4, 5, 6, and ran out of space, so I had to draw this and come back around here in order to go into evaporator 7, 8, 9, and 10. So we've drawn the system here and we've labeled the feed composition. Now we're going to make use of additional information that's available in the problem statement to reduce the number of variables that are here. We're going to have to go back and reread it, which is a common thing you'll do when working mass balance problems. You'll read the problem statement once, work on drawing the process flow diagram, putting all the information into it, and then once you get past an initial drawing of it, you're going to go back and reread the problem statement to make sure you didn't miss something, or there's additional information you can use. So the very first thing that you should do when working these problems is ask, are there any flows that have been specified? In this case, no flows have been set. So we're free to choose one of these flows and set it to an arbitrary value. And what we're going to do is set the feed flow to 100. I'm just going to assume that's going to be 100 here because up to this point, none of the flows have been specified. This represents a basis for the calculation. If at some later point we're told the feed flow rate is 50 instead of 100, we can take the results that we get for a feed flow rate of 100, the results for the flow rates, and just divide all the flow rates by 2 in order to get the results for 50 from the results for 100. And so all the flows will scale depending upon how we change the feed flow rate from 100. So if we increase it by a factor of 2, all the flow rates will increase by a factor of 2. If we reduce it by a factor of 2, they all reduce by a factor of 2. Let's go back and reread that problem statement and see if there's additional information we can use. Well, there is, and the very first piece of information is in the yellow right here, is that the brine from the 10th contains 5% mass by salt. What that means is that the mass fraction of salt from the 10th is 0.05. So we can put that in our process flow diagram. So this is a repeat of that statement, that the brine from the 10th evaporator contains 5% salt. So the mass fraction of salt in that stream, which is X10, is 0.05. And we can compute the mass fraction of water by taking 1 minus 0.05, and we get 0.95. So we made use of that additional specification from the problem statement. Once again, let's go back. We know there's one other bullet there that we might be able to make use of in order to reduce the number of unknowns that we have here in the process flow diagram. Because right now we have a whole bunch. We have 10 of these MEs that we don't know, ME1 through ME10. That's a lot of unknowns there. And we also don't know the X1s through the X9s now. So there's 9 of these X's that we don't know. So if there's any way we can reduce the number of unknowns, that would really be helpful. Well, it turns out this last statement dramatically reduces the number of unknowns. What we're going to do is assume that each evaporator produces the same flow rate of water vapor. Wow, that's great. That means the mass evaporated from 1 is equal to the mass evaporated from 2 equals the mass evaporated from 3 is equal to blah, 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 for the rest up to the mass evaporated from 10. They're all equal. So instead of having 10 unknowns, we're just going to have 1. Let's update our process flow diagram with that. And so what's shown here is the updated process flow diagram where ME1's just been replaced by ME. Down here in the lower right-hand corner is the statement that indication that for all the MEs, we're going to use this one variable, ME without a number after it. So ME1 is ME, ME2 is ME, etc. until we get to ME10, which is also ME. So now we've made use of all the information that was available in the process flow diagram. Let's see if we can solve for any of the other unknowns that are in this diagram. In order to evaluate if we can solve for any of the unknowns, we're going to perform a degree of freedom analysis for a control volume that surrounds the entire process, for a control volume around the overall process. Where we start here, we don't know. Where we should start, we don't know. This is a common issue you're going to face with solving multiple unit mass balance problems. You don't know which one to consider first, which control volume to consider first, the overall or a control volume around any one of the units. We just don't know which one will be the easiest to solve or even possible to solve. So what we have to do is try one. If it works out, great. If not, then we'll try another one. We know that we can draw a control volume around each of the process units. And so if the first one doesn't work, then we'll go on to the second, third, fourth, etc. So let's try, instead of around an individual unit, let's try around the overall process. So what's shown here is a shrunken down process flow diagram, which we put all 10 evaporators into a row there. And the red box around it is our control volume. And so what I'd like for you to do is take a moment and go around this control volume. And for each stream that crosses the boundary of that control volume, identify the unknowns that are present in it, and the components. You're going to put the unknowns in the table that you see down here in this cell in that table. Just list them out so we can count how many unknowns we have. And you're also going to put down the components that are present in those streams in this cell here underneath equations, because we know that for this steady state non-reactive process, the number of equations is going to be equal to the number of unknowns. So I'd like for you to do that. I'm going to pause here just for a second so it gives you time to stop the presentation and fill in this table. So please stop the presentation now and fill in the table. Well, I hope that you did take time to fill in the table, because now I'm going to fill it in together with you. So what we're going to do is we're going to start on the far left where the feed comes in, right here, the stream right here. That crosses the control volume boundary. Looking at that stream, there are no unknowns, so I'm not going to add to that cell, but there are two components, salt and water. And in fact, I already know that all the streams that cross that control volume boundary, as well as all the streams that are inside, can have only salt and water in them, in each of them. So this component list we have here of salt and water will not change as we go around the control volume. So we have a total of two components, so that means we have two independent equations. Let's see if we're lucky enough for this control volume to have only two unknowns. So let's move counterclockwise or clockwise around the control volume. The next stream that crosses the boundary is this stream right here. And then there's one unknown, which is ME, associated with the flow rate, and there are no unknowns associated with the composition. Continuing in the clockwise direction, the next stream is the vapor produced by evaporator 2. It has only one unknown, the flow rate, and I've already got it listed here, ME, so I don't have to add anything to it. Looks like this may be something that repeats itself, and we may not have a whole lot of unknowns associated with all these evaporated water streams that cross the control volume. So look at evaporator 3, only one unknown, ME, it's already in the table. Don't need to add anything. Same thing with 4. If I look at the stream, the evaporated water stream produced by 4, there's only one unknown, ME, it's in the table. And in fact, for 5, 6, 7, 8, 9, and 10, all those streams cross the control volume, but there's only one unknown associated with each of those streams, and it's the same unknown, ME. So I only have one unknown that appears in this table here. We're not quite done yet. Let's continue around in the clockwise direction, our control volume here, and we have one more stream that crosses it, the stream right here. And there's one unknown associated with it, which is the brine produced by the 10th evaporator. So looking at this table here, there are two unknowns associated with the streams that cross the overall control volume, and there's two equations we can write because there's two components. So we can solve for those two unknowns by writing mass balances, a combination of the overall balance, or a balance for the salt component, or a balance for the water component. And we're going to do that. Before writing those component balances down, the overall balance, just going to tidy up our little diagram here, our table, just to show you that we have two unknowns, ME and MB10, and there's two components, so there's two equations. We have a salt component and a water component. Now what I'd like for you to do is let's consider a control volume, let's say around the first 4 evaporators instead of overall control volume. Can we solve for the unknowns associated with that control volume? So I've drawn a control volume around the first 4, and I've blown it up a little bit. I've eliminated the evaporators beyond the 6th evaporator. I'd like for you to do the same thing that we did for the overall. Go around this control volume, identify all the unknowns associated with the streams that cross the control volume, and then identify the components that are in those streams. I think we can safe to say that there's only going to be two components, again, salt and water, so there's two equations we can write. But how have the number of unknowns changed? I'd like for you to take a moment to fill in this table by going around the control volume and identifying the unknowns associated with each of the streams that cross that control volume. Well, I hope you took time to do that. If not, press pause, press stop right now and do so, because I think it's the way you're going to learn is to do it on your own and then working it together here in this lecture. Well, let's start again with the feed. Over here on the far left, that's the one stream that crosses the control volume. There's no unknowns associated with it. I'm going to speed things up a little bit. We know that for all the streams that cross the upper boundary of this control volume, that all the evaporated water streams that cross the upper boundary, there's only one unknown associated with all of them. If you see all 10 of them, there's also only one associated with the first 4 of them, and that's the amount of water that's evaporated, ME. That's the only unknown that's associated with those 4 streams that exit the top of the control volume there. The last stream we have to consider is the brine that's produced by the fourth evaporator, which leaves. And looking at that stream, we have 2 unknowns associated with it. The brine from the fourth, which is MB4, and the composition of that brine, the salt composition, which is X4. It's mass fraction of salt in the brine produced from the fourth evaporator. So we have 3 unknowns here. And unfortunately, if we consider 4 evaporators, there's no way we're going to be able to solve for the 3 unknowns there because we only write 2 equations. There's only 2 components. However, if we write the mass balances for the overall control volume and we're able to solve for ME and M10, then if we go back to the balances that we write for the first 4 evaporators, ME no longer will be an unknown, and we'll reduce the number of unknowns to 2. And from the 2 equations that we can write for salt and water, or we can substitute the overall for either the salt or water, we'll be able to solve for those 2 unknowns. We're going to go through the process of solving the mass balances for the overall control volume next. And before doing so, I just want to tidy up the table here to show that we do have the 3 unknowns, ME, MB4, and X4. And there's 2 components that are present in those streams, salt and water. So we're going to solve those control volume for the unknowns associated with the overall control volume. And then from that, we're going to calculate the fraction of the seawater that's recovered as drinking water. And what we should find is that the mass flow rate of water evaporated is 3 for each of the 10 evaporators. So the fraction of the seawater that we recover as drinking water is the total flow rate of the evaporated water, which is 10 times the flow rate from each, divided by the seawater feed, which is 100. And if we take 10 times 3, which is the ME, we get 30. We'll get 30 here. 30 over 100 is 0.3. So let's go through that process. So we're going to write the balances for this control volume around the overall process. We have the ability to write 3 different balances, an overall balance, and then a balance for each of the components, in this case salt and water. Now of these 3, only 2 are independent. And the reason we write the third one, in this case, well, the independent balances are for each component. The reason we write the overall balance, which is not independent, it's the sum of the component balances, is that it's often easier to solve. So although we're writing down 3, we realize only 2 of those are independent. And I've reproduced the overall process here and the control volume around the overall process to help guide us in writing these balances, which for the steady state, non-reactive process are going to be of the form that what comes in is equal to what comes out. I'd like for you to now pause this presentation and then write these balances out on your own. Attempt to write them out. I think you're going to find that they're a lot easier to write than it might appear at first glance. There's a lot of streams, that are crossing this control volume, a lot of process units, so it may seem like it's going to take a lot of work and be very tedious, but it turns out to be pretty easy. So pause this presentation and take a few minutes to write out these balances. Well, we're going to continue now, and I'm going to write them out with you. I hope you had taken time to do this on your own before watching this. Okay, let's start with the overall balance. We're going to say that what comes in is equal to what comes out, and for this control volume, and we're going to start with the feed stream to this process over here on the far left. So the overall balance is going to be the total amount that comes in, which is 100. That's an input, so we'll put that here on the left-hand side of the equals. And we're done with that stream. That's the total amount that comes in. Now we're going to proceed clockwise around the control volume and look at each of the streams that cross the top of this control volume, which are the streams associated with the water, the pure water, which is our product that's being evaporated from each of the evaporators. It turns out that if we look at these, the total flow rate of each of these streams is the same, ME. So the total amount that leaves, that we will have to count as an output from this control volume, the total amount that is coming out will simply be the number of those streams times the flow rate. So we have 10, and we'll multiply that by the flow rate, ME. So total amount that comes out of this control volume that's associated with those 10 evaporators, the evaporated water from those 10 evaporators is just 10 times ME. Let's continue around clockwise. The only other stream that crosses this control volume is the brine product that's produced from the 10th evaporator, and the total flow rate of that stream is MB10. So we've written the overall balance for this control volume. We've written it, this balance, overall balance in the form that what comes in is equal to what comes out. Now let's do the same thing for salt and water, each of the components. Having written the overall balance, we can use that as a template for writing the component balances. All we have to do is take the flows associated with the inputs and outputs to this control volume and multiply each of those flows by the fraction of that component that's in that stream. So for instance, let's start here on the input side. We have 100 total coming in. In order to do a salt balance, I have to multiply that 100 by the fraction, which is salt. And I can look over in the table here, or on the process flow diagram, and I see it's 0.035. It has a mass fraction of salt of 0.035. So the total flow rate, which is 100, times the fraction, which is salt, gives me the amount of salt that's an input to that control volume. There are no other inputs that we identified when we did the overall balance, so we're just going to set that equal to the output. And we're going to take each of the outputs, the first one is 10 times ME, and multiply that by the fraction of that stream, which is salt. This is the evaporated water produced from the 10 different evaporators, and there's no salt in any of those streams. So we're going to multiply that by 0. That whole term then goes to 0. It's not present. We have to add to it the amount of salt that's in the other output stream, which is MB10. And we're going to multiply that by the fraction of this stream, which is salt. And we know that's 0.05. Turns out, if we look at the salt balance over here on the left, what comes in, we know, we can calculate. And what comes out is just this one term, which has one unknown in it, which we can solve for. So this is the equation we'll probably solve first for one of the unknowns. Let's move on to the water balance. Once again, we'll take the total amount that comes in and multiply it by the fraction, which is water, which is 0.965 from the table above, from the process flow diagram above. Or if we had a stream table, we'd take it from the stream table. We'll set that equal to what comes out. Well, one stream that comes out is this evaporated water. The total flow rate from all 10 evaporators is 10 times ME, and the composition of that, the mass fraction, which is water, is 1. So I'll put a 1 there. And I'll have to add to it the water that comes out in the brine from the 10th evaporator. So I'll take the flow rate, which is MB10, and multiply it by the fraction, which is water, which is 0.95. That comes from our process flow diagram here. So we've written the water balance, and if we look at this, we'll see that in this equation we have two unknowns over here. associated with the outputs. So this equation can't be solved for one of the unknowns, just like the overall balance, which has both of those unknowns in it as well. Fortunately, though, this one here in the middle, the salt balance, is one that we can easily solve for the flow rate of the brine coming from the 10th evaporator. And this will keep us from having to solve two equations and two unknowns. So before solving for the unknowns here, I'm just going to tidy up the equations. You can see that in this table here, we have the input to the control volume, what comes in, the overall amount, the amount associated with the salt, the amount associated with the water. And on the right-hand side of the equals, we have the output from the control volume, the total amount that comes out, the overall balance, the balance for salt, and then the balance for water. And it's this equation right here that 100 times 0.035, which is 100 times that is 3.5, is going to be equal to 0.05 times MB10. So MB10 is 3.5 over 0.05. So if you do that, you get 70. I've tidied that up here for you. That MB10 is just 100 times 0.035 divided by 0.05. That's equal to 70. We can calculate ME from the overall balance. So ME is just going to be 100 minus MB10. And then we divide that by 10. So just rearranging this equation to solve for ME. ME is 100, or equal to, in parentheses, 100 minus MB10 divided by 10. It's 100 minus 70 divided by 10. That's just 3. And that was indeed what we're told the answer is that the flow rate of evaporated water from each of the evaporators, which is the same for each of the evaporators, is 3. So the fraction of water you recover from your feed is 10 times ME divided by the feed. It's 10 times 3 divided by 100. The fraction is 0.3, or you can write this as 30%. And so with that, we solve for the unknowns associated with the overall control volume, and you should be able to then go back to the balances that we wrote for evaporator 4 and solve for the unknowns associated with it. Or if you look at any of the other evaporators, you'll be able to solve for the unknowns associated with any of the other evaporators as well. That's it for now.